Dos.
Well, welcome to the third plenary session of the annual meeting of the Mexican section of the Society for Industrial and Applied Mathematics. Today, we have the pleasure of presenting to you a talk by Dr. Pablo Marquet from the Departamento de Ecología de la Pontificia Universidad Católica de Chile. Pablo, I met Pablo many years ago. He's somebody very special. He's a biologist. He has a lot of curiosity and inquisitive mind. He has explored areas of ecology, not only applied ecology and field ecology. He goes to the fields and samples and does whatever the ecologists do there. And also exploring theory, mixing and incorporating ideas from anthropology, the use of mathematics, physics concepts, complex systems. And besides these qualities, he's also an excellent cook and a connoisseur of wine, particularly Chilean, which is very good, particularly when you visit him or you have a meeting with him. He's really stupendous host. And from the more formal side, Pablo Marquet is director of the Department of Ecology of Pontificia Universidad Católica de Chile. He's a biologist, amply recognized for his contributions in the fields of macroecology, theoretical ecology, conservation and global change, the scaling of abundance in communities, the evolution of body size on land masses, connecting body size to area, evolution and fitness, metapopulation models in dynamic landscapes, the emergence of power laws in ecology and social complexity, and the impact of climate change upon biodiversity. He is fellow of the Ecological Society of America, a member of the Chilean Academy of Sciences, of the National Academy of Sciences, of the American Academy of Arts and Sciences, of the World Academy of Sciences. His program, the research program, has a central aim to understand biological complexity using tools from mathematics, physics, biology, and anthropology. So without more to say, which is really the talk which is coming, it will be, I hope, very interesting to all of us. So Pablo, the screen and the audience is yours. Thank you for sharing your ideas with us.
Thank you, Jorge. It's a pleasure to be in Mexico, even though not my perfect way of being there, but at least the pixels will suffice for the moment. And what I'm going to talk today is about the integration of theories. I think that's something I've been pursuing for a while. And I'm going to give you example from ecology, but that this is something that is very well documented in physics and other sciences. How we integrate theories, why we should aim at integration. And look that I'm not requesting or talking about unification, because I think that integration is a most modest research program that have to be accomplished before you can even think of unifying things. And you have to make to actually make the point that these theories should be at some point compatible. You cannot contradict or have contradicting theories. And we started working on this as a consequence of a series of workshops that happened almost 10 years ago. A group of people came together to analyze the current state of theories in ecology, and in particular, a couple of theories which were the theory of metabolic theory of ecology, neutral theory, and also the MexSIAM theory of ecology, and trait-based theories in ecology. So we were trying to think of how these theories can talk to each other and can actually enrich each other. And in doing so, we realized that we need to start helping or organizing our thoughts about what a theory is. Because pretty much there is a lot of confusion and problem with that. As a result of this, we published this paper where is the essence of what we postulated theory should be in ecology, and we have a group that meet regularly or each 2 years to discuss these issues, and we have this network which is called the Network for Ecological Theory Integration. But let me start briefly what a theory is. And a theory, there are three main views in general, the syntactical or received view of theories, which pretty much comes from the logic positivistic school, where theories were kind of calculi, logical reconstructions, a very kind of interest in doing this in a mathematical, logical way. But this was a view of theory that was abandoned because symbolic logic was not appropriate formalism for theory, especially back in the 30s with all what happened with the undecibility problems put forward and analyzed by Gödel, Turing, Church, and others. So there is this semantic view of theories, which where they are identified by or they stand. This is the conception that theories stand in a mapping relation to phenomena. So the interest in this view is pretty much that the theories can be identified or have or they reach out to the world through semantically meaningful mathematical models. So a theory is something that stands in relation to nature or to the rest of nature, and models mediate that relationship. And then you have the pragmatic view, which pretty much asks about the internal complexity in theories, and also about the historical development, the role of serendipities. For example, what was the role of Fisher stay at Rob Hansen's experimental station, and how that shaped his ideas about population genetics and evolution, for example. So what we claim, or we actually adhere to the semantic view. That's our kind of the point of our departure for this. So theory, we say, well, theories are inherently deductive, and it's a hierarchical framework that contain clearly formulated postulates based on minimal set of assumptions. And we have to make a distinction between that, which is inherently deductive, from the discovery of new empirical and statistical patterns and statistical relationship, which is very common in ecology, that may often lead to some theoretical advances, but in themselves, they do not constitute a theory. And neither do a statistical representation of data or model fitting exercise. And why we say so, because there is this huge confusion in ecology that everything is called a theory. And it seems that ecology is theory rich. If you do a search in this web of science, as we did back in the 2014, there were at least 78 theories in ecology. And from life history theory, which is one of the most cited, optimal foraging theory, metabolic theory, ecology, competition theory, back to gap theory, Fisher-sex ratio theory, landscape theory, etc. So everything look like has the right to be called a theory, but the problem is that we are somehow confusing theory with models. And models are usually intended to increase our understanding of particular problems. As I say, from the semantic view, is a way of relating to the world and increase our knowledge of some particular interesting part of it. But in itself, they do not constitute a theory. So they allow us to explore consequences of relaxing one or more assumptions of a theory, but they are not theories in themselves. And as has been put in this citation by Leon, since models are simplified partial statement of theories, several models may belong to the same theory and are designed to elucidate different aspects of it. So just thinking of this citation, you can think of, if models are related to theories, models should be able to be integrated also to make sense of theories. And now, once we know a little bit about what theory is, when we have competing theories going on in ecology, the problem is how you decide among theories. And here I'm going to use what Larry Loudon, a philosopher of science from Berkeley, said in terms of Wood's theory. And he said that Wood's theory is more efficient than its rival. So it makes more and better explanation and prediction with the same number of parameter of constructs. So he said that this evaluation of theory have to be a comparative matter, and one important criteria for comparison is efficiency. So an efficiency is related how much you can predict with how many free parameters in your theory. So what we claim is in ecology, and I'm going to go very quick about that because I just want to get to the point where we mentioned the central role of mathematics, is that efficient theory should be built as much as possible on first principles. And first principles, I think this is a very important thing because it's core knowledge. I mean, it's well-established, so principles with well-established validity, both theoretical and empirical, is like the foundation of anything have to be first principles, because otherwise you are building theories based on, on the smoke, basically, which is something that might happen a lot in ecology. So, and the importance of this, for example, some first principle could be stochasticity, birth and death processes, Arrhenius equations in terms of speaking about the role of temperature in affecting the dynamics of chemical relationships. I mean, those are core knowledge processes that have ample validity in terms of their operation or their generality. So, and it's important to build on those because they can foster integration among theories that share similar first principles, and also because their application will lead logically to the structure of a theory and to a priori prediction that will be a logical consequence of the operation of the first principles in a given context of a theory. So these efficient theories should be usually, and I say no, but not always expressed in the language of mathematics. Not always means that a theory eventually could not be expressed in the language of mathematics, but it should eventually get there as it matures, as it happens with evolutionary theory, population genetics, and so on. So also efficient theories entail as few assumptions as possible per free parameter, and in that sense, theory should be kind of compressed version of reality, where you don't want to have all the complexity of the theory, but you have to be able to capture the essential part of the phenomena you want to explain. And also, it should not be, well, it will be wonderful if a theory could capture everything, but in practice, you always gets part of the picture only. So we have to value this approximation because it's a way of reaching out and approaching reality. So they also provide standard in which we can compare reality, and they should be effective, in terms of magnify our understanding, help supply legitimate explanation, and assist in formulating prediction. So this is kind of fundamental. But let me go into this issue of efficient theory should be expressed in mathematical language. And here I want to make a little detour to Martin Heidegger, the famous German philosopher. In an essay he wrote in 1962 on modern science, metaphysics, and mathematics, he said that one of the highlights or quintessential characteristics of modern science was that being based on the mathematical language, and he defined what the mathematical is as one of the main axes in knowledge based on the Greek word ta mathemata, which basically means that the mathematical stem from this ta mathematica, which means that is allude to something that can be learned and at the same time can be taught. And I think this is very interesting because somehow it's saying, it's a way of talking about the world that you can apprise, you can learn from it, and you can communicate it in an effective way. So mathematics as a language for science allows you to reduce confusion, reduce ambiguity, gather notwithstanding, but at least it is much better than a natural language. And just to illustrate the role of mathematics in ecology and how it might foster integration, I want to give you an example, which will be the core part of this talk, which is something that we know very well, is this relationship. You know, there's a very simple allometric relationship between S, the number of species, A, the area, and K, the exponent, to which area is raised to actually account for variations in the number of species with area. This was first postulated in print, at least in a journal in 1963. It was early on postulated by someone working on a PhD dissertation in the Caribbean, never published though, but there was this dissertation. But was MacArthur and Wilson who actually put this in mathematical terms. And MacArthur, by that time, by the late 60s, MacArthur had a group of people which was called the Marlborough Circle. It was MacArthur, Lewontin, Egbert Lee, Richard Levins too, and they usually get together in Marlborough, the city in the East Coast, and discuss a research program to put ecology in a more mathematical, quantitative way. And as a result, this development and all MacArthur niche models and competition models that came out from it, as well as Richard Levin's meta-population models and so on and so forth. So it was very productive, and they did constructed the mathematical foundations. And part of the foundation was this equilibrium theory of insular biogeography, or zoography, as they call it in the minute. And it was the monograph of population biology #1, a great monograph indeed. So basically what we ecologists are taught is kind of summarizing this picture. We say, well, you have on the x-axis number of species, and on the y-axis you have rates, and you have the equilibrium theory tells you that as you will have an equilibrium number of species in a given island, which will be the result of this opposing rate. One is the rate of colonization that is decreasing with one, and the other is a rate of extinction that increases as you have more species in a given island. And the colonization decreases because as time goes by, you actually eventually have all the species that can possibly reach that island. And the equilibration among the two, I'll give you this number. No? What we don't realize most of the time is that the model behind it was this kind of a master equation here that expressed the flow is the probability of finding S species at time t, which is based on these transitions that you have S -1, and there is a colonization that you have S +1, and there's death or nothing happened because you already have S species. So they didn't solve this equation actually in the book. They kind of explore some sort of the moments of this, but they didn't want to give or discuss if there was an invariant, how was it, and so on and so forth, or give particular structure to this rate. And that was very, very interesting. But this is the equation for the change in numbers of species in a particular island, which doesn't appear here in the subscript. So it was very, very general. A long time came by, and then in the monograph number 32, Stephen Hubble came out with this unified neutral theory of biodiversity and biogeography that basically takes the same equation, the same master equation, and for observing now is the probability of observing K species with N individuals. Okay, so now we are going back to individual death and birth instead of species kind of colonization and extinction. But the equation is actually the same. So you have n-1, then you have a birth, you have n+1, you have a death, and then you have you already have n, so nothing happened. So they solved this equation, which is a classical birth and death process, and they further assume that birth and death were just linear relationship. There was density independence, so there was in linear relationship with number of individuals in the system, and from there you obtain Fisher-Log series distribution, making these assumptions which explain the number of individuals per species in an ecological community. So basically, Hubble took McCarthy and Wilson and reduced it to individuals and said that all individuals are basically equals in their rates of birth and death. That's why the theory is called neutral. But also, remember that McCarthy and Wilson already had a neutral theory because they also assumed that colonization and extinction were similar, even though they didn't develop the consequences of that fact. Hubble did, and he showed that it can lead to Fisher-Log series distribution. This was interesting. So we have two master equations, one then for the island. Okay, so this is the jump in this stochastic process is basically in the number of species. And here we have another one, which the jump is in the number of individuals. Here is the magic of mathematics that tells you that this cannot be true at the same time. So they cannot coexist because unless a species or unless a species abundance or unless each species is represented by just one individual. Otherwise, you will have a combination, an infinite combination of a number of individuals to actually choose from and do the other. So this will be very unlikely to actually happen. So let me give you the explanation. As you might know, is that the transitions here, the jumps happen in exponential times. So if you have a species, you can go s-1, for example, through time at times that will be exponential. This thing will actually jump here to a decrease with this probability, and here to an increase in the number of species with this probability. So this cannot be the same if you do have the number of individuals, because basically the process, one of these processes should not be Markovian. So if it's Markovian here, it cannot be the other, and if it's this, it cannot be in the other. So basically, we are caught somehow in that the dynamics at the level of individual is actually not compatible with the dynamics at the level of a species. So and as we wrote about this in this book, the one process could be Markovian, but the other should be, by definition, will be not Markovian. So because there will be kind of an impossibility, and you can't kind of explain it. Is you say, if you define a stochastic process like ST here, just in the indicative function, you just add up and you sum species. This vector will actually be a lot to choose from because you will have many combinations of number of individuals that will add up to species that you might have in a given system. So in that sense, ST is a function of a Markov process, but it's not a Markov process itself. So there are solutions to that. Actually, Richter, Dean, and some other have provide insights on this in the distribution, on this distribution, but or how to solve this problem. But the most simple one, I guess, is to actually change the paradigm a little bit, and instead of working on with these master equations in numbers of individuals, we can go to diffusion processes. And here's when things start getting very interesting, because then you realize that the one that started with this, at least in biology, were Seward Wright and Ronald Fisher back in the 30s, and Andrei Kolmogorov, who actually developed the theory back in the 30s and interacted with these two guys too in order to show them the proper way of actually doing these calculations. Although they are pretty much make long strides into this. So I'm here. One of the results is the infinite island model by Seward Wright. Seward Wright always thought of a population being kind of composed of having a special structure, you know. So he thought of local population interacting, exchanging individuals, and eventually, if you have an overall frequency of a particular gene or mutation rate and a given migration between local populations, you can predict the frequency of a gene in any one of them using, he derived this, which is a beta distribution. So, so that was kind of a quintessential model for the genetics of populations, and basically allow what it does. It goes, instead of going to or keeping attached to numbers, it goes to frequency. So that's what we did. Instead of getting attached to numbers or the master equation for number of individuals or number of species, and finding that there is a mathematical discrepancy there, you can actually move into a more continuous description of the phenomena using diffusion approximations. And here, as always, you need good mathematics and good friends, or both. And this is a good mathematician friend who actually worked on martingale and stochastic processes school in France, and provided some of the theorems that we use to actually move from this continuous to the this discrete to the continuous formulation in a way that is mathematically rigorous and straightforward. So basically, the approach is you take an open system approach. So you think that you say, well, we are working with a part of the universe here. This is suppose our community, you know, and this community has boundaries that most of the time are arbitrary, and there are things outside the system that affect and generate fluctuations in it. Okay, so basically what you're saying, what we are saying is that there are things that occur outside, but also things that we don't know may be happening inside the system, and all those are going to be put into the noises. And we're going to have a birth-death process here where the rates are going to be going to have this kind of a structure. So are the birth plus something and the death plus something, and that something that C here is essential because it's everything that might affect birth and death that is actually not accountable for. So it's something that we don't know what it is. So that's this could be density dependence, density independence. It could be interaction with other species, you name it. So we put that everything on the noises, and then we give some particular structure to these rates based on known processes going on in ecology in terms of pretty much following early development in neutral theories of how you will model birth and death processes. So as you see here, C goes into this stochastic differential equation that describe the process, and eventually what we say is that as the number of individuals go to infinity, the dynamic converges to this equation, and as time goes to infinity, eventually you reach a particular invariant distribution that we show is a beta distribution. So interestingly, by using diffusions and by going into this continuous formulation, we are showing that the dynamics that governs that governs the numbers of, or the proportion of individuals among a species is the same one that is governing the proportion of genes within population. This is a one-dimensional diffusion result only, but it can be, since species are neutral, since all the species are somehow equal, what we are basically saying is that they should apply to any species. So that's why from here, we can fit this to known distributions. And here are some fits to fit to Amazon birds, butterflies, tropical trees, coral reefs, basically. And the fit is really good, as good or better than the one that you can do using numbers of individuals and neutral theory or the log series distribution. And but also the parameters here, alpha and beta, have some interesting explanation. Alpha is related to dispersal, as we have shown, and beta is related to speciation, because give you the probability of observing a species in the large limit and a new species in the large limit. And the only way you can do that is by speciation, because if you are in a more local situation, species arise because they come from somewhere else, or because you have a speciation. But in the very large limit, it's only a speciation, the one that is driving the process of new species showing up in your system. So this is the relationship between alpha and beta. And as you can see here, birds communities and marine community have large alpha. Some of them have large beta too. So there is a nice relationship. And here is the relationship between this beta parameter and the theta parameter in neutral theory, which is basically associated with the speciation events. So we have eventually a theory that might eventually lead to the integration between dynamics that you observe at the level of individuals and dynamics that you can observe at the level of a species or of genes, excuse me. So, and this actually takes on what Janis Antonovic has been claiming for a long time, making strong parallels between what was going on in genetics and what was going on in communities. Neutral theory is one of those constructs that allow us to move from one to the other, but also I think that using diffusion approximations, it could be leads to, we can show that we get the same invariant distribution. And he says, that the forces maintaining species diversity and genetic diversity are very similar, and an understanding of community structure will come from the consideration of this kind of distinct diversity interact. And we have somehow lead to a little bit of the integration of these two just by working on mathematics and just making the point how important is mathematics for the integration of theory, because it can detect anomalies and it can provide insights into how to solve them. So we are stretching now this analogy, and it turns out that, as I mentioned, the agnobiography theory using this master equation, it didn't want to, or McCarthy and Wilson didn't actually went and look for what we call the distribution of richness, which is what the theory of the solving the master equation for the agnobiography will provide you. Will provide you with the invariant distribution of observing S species across communities. We have done that for data from birds and mammal species across islands of the world. And this is the so-called proportional species richness distribution. And we just take the proportions of the observed in terms of the total number of species known of birds and known and no mammals, and you see that we provide good a good first with fits to this distribution. So it looks like what might be going on at the level of genes within individuals, or at the level of individuals within a species, and also at the level of species within communities, can be very well described by this approximation. But we can go a little bit further and now ask, would this work to understand the dynamics of genes within genomes, which is another level of this is the lower level of organization. So, and the abundance of these gene families within genomes, that's what we will focus on. And the analogy is very interesting because birth-death processes has been applied to understand these distributions. The driving processes are similar. You have duplication, you have mutation, you have lateral genes transfer, retroviral infection, which is like colonization thing. You have also plasmid and exchange and also gene extinction. And so we developed a model applied to genes and provide predictions and for genes families. And here is some fits for the beta distribution to the relative abundance of protein families in bacteria and eukarya, according to one of the classical classification for protein families. And we're talking about 7,600 bacterial proteinomes, 11,000 families, and 30 million genes. And as you can see here, the beta distribution fit is very good, and provides, when you do this, you can compute the alpha and the betas, and it gives you a panorama of alpha and beta, which identify clusters of species. As you would expect, bacteria, which is here in gray, are the ones that can reach out the highest beta and the highest alpha. Alpha was associated to dispersal and beta to speciation. So we have continued doing this and doing this fit for the distribution of gene families and proteins across the history of life, pretty much. And so far, the results are very kind of encouraging in terms of providing us with a very good fit. But the most important part is that somehow genes within genomes, and these genomes eventually within individuals, and individuals within a species, and a species within communities, when you look them through the right model or processes, you find that you can integrate across these levels of organization. And it seems that there are some very fundamental processes going on, providing structure to these entities at these different levels that are very similar in an essence. So by integrating this series within genomes, or what we thought about species dynamics and abundance dynamics, we are somehow moving, I think, biology into a more integrative understanding of the entities usually it works with. So this being said, I just want to thank my collaborators and to you for being here and this talk. Thank you very much.
Thank you, Pablo. Very interesting indeed. We can open for questions. You can raise your hand in the lower part of the screen, or type your question in the Q&A icon that is there. Are there any questions? Questions? I have a question while people is writing, I guess. Pablo, a question.
Good.
Okay, one question is the following. I was thinking you are showing a kind of pattern of regularity in this structure, this hierarchy within genomes and genes and populations and individuals and communities, and they are described more or less by the same kind of process. But all these, for example, at ecological level, involve interactions, ecological interactions. The implication will be that this ecological interaction, either predation or competition, have also some kind of regularity, right? Because when you average over all this, you are saying they behave essentially the same across hierarchies. So there must exist some regularity, or what is your point of view with respect of this?
Well, thank you for the question, Jorge. I think it's a fundamental one. First, if you start working at the level of genomes and showing that they show patterns that are similar to or the same as the one that you see at the level of communities, then you can claim, and I usually do that everything is ecology. So because you have interactions, you have exchange of matter, energy, and you have birth and death of the entities you are working with, and that's fundamental. So first thing, there is some kind of we can integrate the way we look at these systems. And the way we look at it is by dividing it into different disciplines: the geneticists, the molecular biology, the ecologists, and there might be something more fundamental that unifies across levels. Second, maybe the levels of organization metaphor is like a straitjacket that we have to actually give away at some point, because it's for some analysis it's not useful. It impedes realizing the unity behind the processes we're talking about. And third, and this goes straight to your question, is the issue of interactions across or within each level. If you go to the upper level, to the ecological communities, yeah, in fact, you have competition going on, you have mutualism, you have predation, but somehow we are using a kind of a neutral description of that. So how it comes that things being different are going to be the same, because that's what neutral theory says. All individuals are identical in their per capita birth and death rates. So how it comes that something that we know are different are going to be the same? And I think that the trick here is not that they are the same, but that they are different to be the same, which is a paradox. Because because the key here is that by being different, you actually, what you do, you equalize fitness. For example, species can be different in terms of the dispersal power. They can move along this RK spectra. Some species are very rapid, fast. They can reach to sites recently reserved, and they can get there before the competitors. So this colonization competition trade-off, for example. So it's a way of being different that actually generates that you equalize your fitness. So fitness equalization is essential, and that's why neutral theory provides a good description of systems that are symmetric in terms of fitness. Because even though they are different, species are different, they are different to actually equalize their fitness. So, and I think that that's happening at all levels, and it have to be that way, because if there is no equalization in fitness, there will not be coexistence. You will eventually reach out monodominance. So in order to keep the system diverse, you have to be doing that. Thank you for the question.
Thank you, Pablo. Are there any more questions? Miguel Ángel Morales. Miguel Ángel, please. I think that, yeah, please go ahead.
Thank you for the talk. I have a question actually from the first part. In developing theories, Nowadays, we have a lot of data. So my question is, what is the role of data in developing a theory? What is your reflection on that? Thank you.
Thank you, Miguel, for your question. I think that is becoming essential in these days of big data to analyze the role of data theory. And there's sort of a tension. And the tension is that at some point we need to know and we need to take informed decisions very quickly. Think of the pandemics we're living through now, and the use of data that you may not completely understand, but it might be very the only thing that you have, because if you don't have a theory that actually will predict that data, you just rely on machine learning or deep learning, and you just fit phenomenological models to data, and you can move forward with that. But I will claim that the best scenario is that we have to move towards theories that will allow us to integrate with other theories, and that will provide more deep understanding of what is really going on. Because otherwise, I mean, we end up with just phenomenology, and that's not bad. It's part of probably the way theories transit, or ideas transit, to become theories and models, and give rise to models to connect to reality. But I will say that we need to have probably a more deep understanding of reality than just big data will provide. Because at some point we have to understand, I mean, probably our biggest concern right now, in addition to the pandemics, but not independent of it is climate change and biodiversity crisis. So we need to understand how the system works in order to preserve and assure its long-term kind of persistence and the interaction to actually regulate between biodiversity and climate, how biodiversity and climate regulate each other. We need to have a theory for that, because that will be essential to inform management policies. We cannot just rely on machine learning for doing that, so that's the urgency too. And the other part of my answer to this is, we are living in very interesting times in terms of, with all this kind of big noise about artificial intelligence, for example, how robots and this kind of softwares are doing hypotheses and even testing hypotheses for humans. And there is something very interesting in what is going on. It looks like we have so much knowledge and so much data about the world that we reach out a limit in terms of how much we can process and make advances of it, and that we have to be held by this artificial intelligence and kind of devices, and that's even more a reason for the need for theories, because theory have to compress reality in a manageable package, and otherwise you have the risk of what this guy Borges, the writer, the Argentinian writer, has a famous tale, or a short novel, I guess, where he described a city near the Pampas in Argentina, where people actually, they made a map of their city that was the same size as the city itself, and that you can still see pieces of that map, moving on along the Pampas, carried out by the wind. So we cannot, obviously, a map the size of the city, once to describe, is useless. So we need to compress the information. Somehow we can manage the complexity of the world and not being overwhelmed by the data. Thank you.
Thank you, Miguel Angel. Thank you, Pablo. Is there any other question? No more questions? Well, if there are no more questions, then we thank Pablo Marquet. Thank you very much, Pablo, for your talk. Very interesting.
Thank you, Jorge.
And things like that. And thank you all for attendance. We have a coffee break now, and we resume with our meeting at 12:30 in the parallel sessions. Thank you very much for your attendance. See you around then. Thank you, Pablo, again. Bye.
Thank you, Jorge. Bye-bye.